Welcome to the Resolution channel. In this video, I'll be looking at the resultant of forces acting in space, and I'm going to be illustrating this using an example. And we're going to walk through this example, given that the cuboid is supported by 3 strings as shown. If the tensions in the strings AB, AC, and AD are 1242 newtons, 5771 newtons, and minus 6480 newtons, respectively, what is the total reaction at point A? Total reaction at point A is just saying what is the resultant of all these forces acting at point A. So A is the point of focus. To address this problem, the first thing to do is to get what you call free body diagram. And free body diagram is different from a space diagram. Like the diagram having all the bodies acting on them. As we can see, the cuboid, the top of the topmost support and the point A, they are all attached together. So this is a space diagram. We're going to start by introducing our Cartesian coordinate system in the 3D. And after that, there are different forces acting at point A. We have first the reaction at point A, which is what we want to look for. We have another force as a result of the string attached to point A and D. Then we have another force of the string attached between point C and A, and a final force of the string attached between points B and A. Now these are the 3 forces, and we have their directions as well. We have the direction of force AB, we have the direction of force AC, and we have the direction of force AD, as well as the direction of the reactions. And that constitutes what you call a free body diagram. Once this is done, one must quickly extract the free body diagram. Once this is done, the next thing to do is to extract the free body diagram and work on each of the forces one at a time. In working on these forces, in order to find the resultant, the best procedure is to take each and all of the forces to their component forms and add up respective components together and bring the components together to get what is called the resultant. And we're going to progress by taking each of the forces to their components, then we add them up eventually. So we're going to quickly start by force B. So if we have force B acting on this system, we want to see how we can easily take force B into its component form. To take force B to its component form, we must be able to identify the different position, that how far this force has been transmitted in each dimensions, and calculate how far this force has been transmitted in each of the coordinates, and calculate the direction cosine for this force. And using the direction cosine, we can quickly take the force to component form. If we look at the diagram that we have, one will discover that for the force to have been transmitted from point A to point B, it has moved in the x-axis, in the y-axis, and in the z-axis. For it to be transmitted from A to B, one can quickly discover that the force has been moved from 0 position to a position along the x-axis, and the distance that it has moved is 3.5 meters. And knowing that it's 3.5 meters, we have that bx is equal to 3.5 meters. But there's also something that is important, the sense. If the force has moved from 0 to A, one can easily tell that it's moving in the opposite direction as the s-axis. That is moving to the left, and the s-axis is pointing to the right. So we have that bs is equal to minus 3.5 meters. Then by the time the force moved from A to B, it has moved along this dimension in the y-axis, and that dimension is given to us as 5 meters. So we have that by is equal to 5 meters as well. But if by is 5 meters, is it going to be plus or minus? That's the sense of by. The sense of by is going to be negative. It's negative because if this force is moving from point A to point B, it would have moved from this point down to the origin, and it's moving downwards, and y-axis is pointing upwards. So because it's moving in the opposite direction of the area that y-axis is pointing, we have a negative sign for by. And finally, bz. By the time this force has moved from this point to this point, it has also moved in the z-axis direction, and it has moved this dimension. And for this case, this dimension is given as 4 meters, as we can see. And if this dimension is given as 4 meters, one would need to quickly note that then bz is equal to 4 meters. But is it positive or negative? If we're moving from the origin, that's from this point A to point B, we discover that this force has moved this dimension and is in the same direction with the z-axis. And because it's the same direction with the z-axis, it's going to be positive. If that is positive, the next thing is to find the dimension of the force, which we call B. We need to quickly look for B. And we said in the video that here we describe how to find direction cosine and how to find component of forces, that B is equal to the square root of all the dimensions that we've estimated plus by square plus bz square, which is equal to, we have our bx to be 3.5, even if you put minus 3.5 square, it's going to be the same, plus minus 5 square plus 4 square, and that is b. The next task will be to look for the direction cosine for the different axes. Cos theta x is equal to bx over b, which is equal to minus 3.5 over square root of 3.5 square plus 5 square plus 4 square, which is equal to, if you estimate that properly, you are likely to get minus 0.4796. And likewise, cos theta y is equal to by over b, which is equal to, we have estimated by to be minus 5. So we have minus 5 over square root of 3.5 square plus 5 square plus 4 square. And this, if you estimate correctly, is likely going to be minus 6852. Minus 0.6852, sorry. And finally, cos theta z is equal to bz over b. And we've estimated z to be 4 earlier, so it becomes 4 over square root of 3.5 square plus 5 square plus 4 square. And this, if you estimate correctly, you're likely going to get 0.5482. TAB. Let's not forget that the goal is to take the force to its component form. And we heard from our question that the tension in the string AB is equal to 1242 newtons. And if you want to take to component form, it's just to multiply TAB times cos theta x plus cos theta y plus cos theta z. And from what we've estimated, we had that cos theta x is minus 0.4796, cos theta y is minus 0.6852, and cos theta z is 0.5482. So one can easily and quickly estimate the value of TAB in its component form to be 1242 multiplied by minus 0.4796 minus 0.6852 and plus 0.5482. So TAB will be equal to minus 595.66I minus 851.02G and plus 6 80.86 K. And this is our tension taken into component form. Next, we would need to take tension of the string attached to point C from point A. Next, we'll need to resolve the tension acting on the string from point A to point C into its component form. And we're going to see how to do that quickly. We must quickly recall that TAC, the value of TAC was given to us as 5771 newtons. But we need other dimensions. We need BX, we need BY, and we need BZ. To estimate this value, we can get that from our diagram. We want to note that for this force to be moving from point A to point C, that is, the force is being transmitted from point A to point C, the force would have moved in the different direction, the X direction, the Y direction, and the Z direction. So we're going to start by seeing the X direction. If this force moved from point A to point B in the X direction, that's this axis, the force would have moved from this point O to this point C, and the distance between O to C in the S direction, from what we can see, is 4 meters. So we have that Bx is equal to 4 meters. We are also to be mindful of its sense. We discover that because this force is pointing this way, it's also in the same direction with the x-axis. So this is going to be plus. The next is By. If the force is transmitted from A to B, the force would have fallen along the y-axis from point A to point 0, and that dimension is 5. And because it's away from the y-axis, we say that this has moved minus 5 meters. And Bz, finally, if the force has moved from point A to point B, if the force has moved from point A to point B in the Z direction, it would have moved along this direction, and to have moved this distance. And this dimension from what we have is 4 meters. And because it's 4 meters, we have Bz to be 4 meters. And it's the same direction. The force has moved from here to here. Obviously, the force has traveled in the positive Z axis. And once all these are obtained, the next thing is to find B. B is same thing as square root of 4 square plus 5 square plus 4 square. And once B is known, we can quickly begin to look for the direction cosine for each and all of these forces. For theta s, we have it to be b over b, bx over b, which is equal to, in this case, is 4 over 4 square plus 5 square plus 4 square, all square roots, and that will be, if you estimate correctly, will give you 0.53. And if you're looking for cos theta y as well, is the value of by divided by b, which is equal to minus 5 divided by square root of 4 square plus 5 square plus 4 square. And this will be, if you estimate correctly, minus 0.66. And finally, cos theta z will be the value of bz divided by b. For this case, bz is 4, so we have 4 over square root of 4 square plus 5 square plus 4 square. And this one, if you estimate correctly, is going to be 0.53. And once all these are known, to take the first two components, TAC, the value of TAC is equal to 5,771 newtons. And of course, vectorial form, if you want to take two different components, you have to multiply this value TAC, that's the magnitude of TAC, which is 5,700 newtons, multiplied by the direction cosine for all the axes, cos theta s, cos theta y, and cos theta z. And this will be equal to 5,771 multiplied by 0.53, which is our cos theta s, and minus 0.66, that's our value of cos theta y, and plus 0.53, that's our value of cos theta z. And once this is done, one can quickly get our value of TAC to be equal to 3058.63 I minus 3808.86 J plus 3058.63 K. And this is the value of tension AC resolved to component form. And finally, we may want to also resolve the last force to its component form before we add them up together to get the reactions at point A. That's the total forces acting at point A or the resultant force acting at point A. And to do this, we need the free body diagram as well. To take the tension TAD rather, which is the tension of the string at the point is attached from A to D to resultant form, we must recall our formula. To take to resultant form, TAD is equal to the magnitude of TAD multiplied by the duration cosine cos theta xi plus cos theta yj plus cos theta zk. Cos theta s will be equal to bx as usual over b. The same vein, cos theta y will be equal to by divided by b, and likewise cos theta z will be equal to bz over b. Our first challenge becomes, how do we get bx, by, bz, and b? Bx, as I've described earlier, is the dimension of which this force was transmitted in the x-axis as it moves from A to B. As this force moves from A to B, we can see the origin O, and we can see this line here. If we have this line, how far has this force been transmitted along the x-axis? For this case, we're given a value of 2.6 meter. So Bx is equal to 2.6 meter. Something else to be mindful of, the sense. Is it going to be positive or negative for this value? For this case, this force is acting this way. So if we resolve this force along the x-axis, it's going to be pointing in the same direction as the x-axis. So for this, we're going to have positive. If we do same for by, by will be the dimension, that's the dimension that this force has been transmitted along the y-axis. For this case, we have that it was transmitted from A to the ground, that's to the base of this object. So we have the force to have been transmitted along the y-axis this distance. And this distance from what we have is 5 meters. And because it's 5 meters, we're going to write by to be equal to 5 meters. The next thing, something to be mindful of, is the sense again. What direction has it been transmitted? We can observe that y is pointing upwards. Well, if this force is transmitted from A down to B, we can see that it will be pointing downwards, which is opposite of the direction that the axis is pointing. So that makes this to be negative. And finally, BZ will be the distance that the force was transmitted along the z-axis. For this case, we have A, which is supposedly at the center of the box, where the force starts its transmission from, down to point D, where it ends. We discover along this line that this force has been moved a particular dimension, which is equivalent to this painted line that is shown on our screen. And the distance of this painted line that we have is same thing as this 4 meters from the dimension that has been given to us. So this force has been transmitted along this axis by 4 meters. So we have our BZ to be 4 meters. But something to be mindful of again, the sense. As we can see, by the time this force starts from the origin, from the top, and it has moved to the base, that's D, it would have moved away from this origin to the base by 4 meters. And one can quickly tell that this force is pointing towards this direction, which is away from the direction that the z-axis is pointing. The z-axis is pointing downwards, while this force is pointing upwards, away. And because it's opposite direction, we have bz to be minus 4. And once that is done, one can quickly find b. B is the square root of the sum of all those components, 2.6 square plus 5 square plus 4 square. And so once b has been estimated, it becomes straightforward to determine the value of the direction cosines for the different axes. For this case, cos theta x, simply as we stated earlier, is bs over b, and bs will be determined to be 2.6 meters. So we have 2.6 divided by square root of 2.6 square plus 5 square plus 4 square, and which will be equal to 0.38 if estimated properly. Then cos theta y, which is the direction cosine in the y-axis, is equivalent to by divided by b, which is equal to minus 5 divided by square root of 2.6 square plus 5 square plus 4 square. And if this is estimated properly, we are likely going to get minus 0.72. And finally, cos theta z, which is equal to bz over b, is equivalent to minus 4 divided by b, which is 2.6 square plus 5 square plus 4 square, which is equal to 0.58 minus 0.58. Having estimated the direction cosine for each of these, if we go back to our equation that is used to calculate, to take the particular component form into to take the tension into component form, we have that TAD therefore will be equal to minus 6480 multiplied by 0.8i minus 0.72j minus 0.58k, and TAD will be equal to minus 24624i plus 4665.6j plus 3750.62k, and this value is our tension TAD taken to component form. So let's quickly bring out all the resolved forces so that we can add them up. We estimated TAB to be equal to minus 595.66i minus 851.02j and plus 680.86k. And our second force, TAC, to be equal to 3058.63i minus 3808.86j plus 3058.63k. And finally, TAD is equal to minus 2.4I plus 4665.6J plus 3750.62. We know that resultant is equal to the sum of the forces TAB plus TAC plus TAD. So our resultants, to find our resultants, we need to add all components that are similar to themselves. So if you add all the I components together to get the X component of our resultants, we are going to have 0.57I approximately. Then if you add all Y components, adding this to this and to this, if you add them up, you are likely going to get plus 5.72J. And finally, all K components, you add them up together, and if this is added, you are likely going to get plus 7490.11K. And to get the value of the resultant, R is equal to square root of Rx square plus Ry square plus Rz square. And this will be equal to square root of 0.57 square plus 5.72 square plus 7490 square, which is equal to approximately 7,490 newtons, and one can say this is also approximately equal to 7.5 kilonewtons. So I want to thank you for watching, and I do hope that the video was illustrative enough. I look forward to seeing you in our next video. Thank you.